Hello folks, I'm going to be going over chapter 3.3. This is covering the Varactor Diode. So we just got done with Zener diodes. So we're going to move on to the Varactor Diode. A few things to note about this is the Varactor Diode is a voltage controlled capacitor. They're commonly used in communication systems. They're also known as varicaps or tuning diodes, and they operate in reverse bias. And as we read through this, you're going to see that the depletion region acts as a dielectric because of its non-conductive characteristics. The P and the N regions act as capacitor plates, as you'll see as we read through this. So the junction capacitance of diodes varies with the amount of reverse bias. Varactor diodes are specially designed to take advantage of this characteristics and are used as voltage control capacitors rather than traditional diodes. These devices are commonly used in communication systems. Varactor diodes are also referred to as varicaps or tuning diodes. So there's several things in here that I mentioned to you up front that you need to remember for a quiz. So just letting you know. So let's talk about exactly what a varactor is. A varactor is a diode that always operates in reverse bias. So it always operates in reverse bias and is doped to maximize the inherent capacitance of the depletion region. So if you look at this symbol here, it stands for variable capacitance. So it says the depletion region acts as a capacitor dielectric because of its non-conductive characteristics. So you see right here it's pointing to this area here, and this depletion region here acts as a dielectric. And a dielectric, if you remember in a capacitor, is almost like an insulator between these two parts. Okay. The P and the N regions are conductive and act as capacitor plates. So basically we have the dielectric in between and we have the plates on either side, just like a capacitor. All right. So the basic operation, recall that capacitance is determined by the parameters of plate area, dielectric constant, and plate separation as expressed in the following formula. So I'm not going to be asking you about this formula, but I want you to understand that, remember in capacitors, the farther away the plates, which way, was it inversely proportional or, proportional to the capacitance? Well, the further away the plates are, then the capacitance goes down. Closer together, capacitance goes up. Just like if the plate area gets larger, then capacitance goes up. If the plate size goes down, then capacitance goes down. So it's just keep it in mind. Just like a capacitor, those same things hold true in a varactor diode. Okay, and this right here is an actual symbol for a varactor diode right here in figure 323. So as the reverse bias voltage increases, the depletion region widens. So as this V bias increases, that means and a reverse bias increases because of that, then this depletion region widens, effectively increasing the plate separation. So basically that means as this right here widens, this area here, that means that the plates are going to get further apart, so to speak. Okay? And when it does that, that decreases the capacitance. Because remember, if the plates get further apart, or if the plate area gets smaller, the capacitance gets smaller. So when the reverse bias voltage decreases, the depletion region narrows, thus increasing the capacitance. This action is shown in figure 322A and B. A graph of diode capacitance CT versus reverse voltage for a certain varactor is shown in figure 3-22C. For this particular device, CT varies from 30 picofarads to slightly less than 4 picofarads, as VR varies from 1 to 30 volts. So if we go to this page, this is what it's talking about. greater reverse bias, less capacitance. So as you see, the VR goes up, so the voltage increases, so the reverse voltage. Then this dielectric widens, which means that there's bigger separation between the plates. Okay, so when the less reverse bias, so when reverse voltage goes down, then this depletion region here, the dielectric, narrows, which makes the capacitance increase. And this chart, like it said, is basically taking the reverse voltage here. So as the reverse voltage goes up, you can see the capacitance goes down. See? So that there's just a chart showing you. So now we're going to talk a little bit about this data sheet here, and then we're going to do some calculations based off this data sheet, and that way you can kind of see, because it's a voltage controlled device, and because the voltage is varied, then we can control, we can have different capacitances, and because of that we're going to be able to calculate what the swing of the capacitance is going to be. Okay, so a partial data sheet for a specific series of Varactor diodes is shown in figure 324. So remember where this is at, 324. It says capacitance tolerance range. Okay, so it says the minimal, nominal, and maximum values of capacitance are shown on this data sheet. So you'll see right here the minimum, nominal, and maximum. So this is the capacitance area here. Here's the different diode types here, the varactors here. And so we're going to be doing an example here. So it says, for example, when reverse biased at 3 volts, the 832A, so let's find 832A, it's right here. Okay. So it should be that one. Can exhibit a capacitance anywhere between 19.8 picofarads and 24.2 picofarads. This tolerance range should not be confused with the range of capacitance values that result from varying the reverse bias as determined by the capacitance ratio. So here's what we're going to be doing, is we're going to be finding out the capacitance ratio, meaning that from this voltage to this voltage, this is how far we can swing. And we're going to be taking information off that data sheet to do so. So what is capacitance ratio? The Varactor capacitance ratio is also known as the tuning ratio. It is the ratio of the diode capacitance at a minimum reverse voltage to the diode capacitance at a maximum reverse voltage. For the Varactor diodes represented in figure 324, which is the data sheet on the previous page, the capacitance ratio is the ratio of C measured at VR of 2 volts divided by C measured at VR of 20 volts. So what that means is that the capacitance at 2 volts and the capacitance at 20 volts. And let me go back to that data sheet. And you'll see right here, capacitance ratio. So C2 is the capacitance at 2 volts, and C20 is the capacitance at 20 volts. So what we're going to be using is this minimum here in our formula, and I'm going to show you. So we're going to be using this number here. That's going to be our ratio. And this number here is going to be the number we're going to put in for the C2. Okay? And you're going to see exactly what we're going to do. So we're going to take this example here. I'm going to explain it a little bit further. So it says here, the capacitance ratio is designated as C2 divided by C20. And it says for the 832A, the minimum capacitance ratio is 5, which I showed you on the data sheet. This means that the capacitance value decreases by a factor of 5 as VR is decreased from 2 to 20 volts. The following calculation illustrates how to use the capacitance ratio, CR, to find the capacitance range for the 832A. If C2 equals 22 picofarads and the minimum CR equals C2 divided by C20 equals 5. So what that's telling us, let me go back over here, it's easier to explain. is we're going to be taking this number here, this nominal capacitance, and we're going to be dividing it by this number here, this 5. This is where they're getting that ratio from. Okay? So we're going to be taking this right here in picofarads. That's key. Don't be just putting in 22 divided by 5. It has to be 22 picofarads divided by 5. Okay? So once we do that, and that is the example they've got set up for us here in the lesson. So if you take so basically we're looking for C20. So it says C20 equals C2 over CR. So we plug in the 22 picofarads for the C2, and then the ratio is going to be plugged in here. So we take those two numbers we found in the data sheet, plug them into this formula, and then what we get, the result we get here, the 4.4 picofarads, is going to be C20. Okay, so that is the range of capacitance based off the voltages between the 2 and 20 volts that come off the data sheet. Okay, so that there, we're going to do a few of these. So this right here again is chapter 3-3, the Varactor Diode. Again, this is a symbol of a Varactor Diode. Okay, here's a few of the notes that we talked about just moments ago. Get that up out of the way. Okay, so remember, it's a voltage control capacitor. It's commonly used in communication systems. It's also known as varicaps or tuning diodes. It operates in reverse bias. Depletion region acts as a dielectric, which is a non-conductive characteristic. And P and N regions act as capacitor plates. All right. So let's go on over here. So here's where we did the first problem earlier. So here is the formula that we looked at in the lesson. So if we want to find the capacitance at 20, then we know what the C2 is. Then we divide C2 by CR, and we can get these two numbers off the data sheet. Okay. So this right here is the one from the lesson. It says calculate using a 832A Varactor diode from figure 324. And again, minimum capacitance ratio is 5. Nominal capacitance is 22 picofarads. Okay, so here is our data sheet. This is exactly what I showed you earlier. Is we're going to be taking this number here out of the nominal, and the other ones that we do here right after we get done with this one, we're going to be taking out of this column, and we're going to be looking in this column, and we're going to be aligning that right there with the correct diode. Okay. So in this one here, we'll go ahead and figure it, even though we already did it in the lesson. So C20 equals, and we have to know what, let me move this down, C2 is. So C2 is going to be the number that you're going to pull out of here, the capacitance. It's going to be the nominal capacitance. Okay, so we're going to put in there 22 picofarads. Now this right here should be an easy one because it's the one out of the book. And then we're going to be dividing that by the turns ratio. This should give us 4.4 picofarads. Okay. So now if we move over to this one, I'd already worked it out for you. So to get C20, we have to put in 33 picofarads. So the C2, so the capacitance at 2 volts nominal. So, and I put that nom in there, just, you don't have to put that in there, but I put it in there so that you would know that you're looking at this. I mean, I figured it may help you. You don't have to put the nom in there, but the C2 over CR is what must be in there. So anyways, we're going to look down through here, and this right here is an 833A. So 833A is going to be 33 picofarads, and we're going to be at a ratio of 5. So we have to take 33 picofarads divided by 5, which should give us 6.6 picofarads. Okay. So now we're going to do this one here. So I haven't done it yet. So we're going to find out what C20 is, what the capacitance is at 20 volts. This is going to be for an 829A. So let's go see what the nominal capacitance is for an 829A. So that is 8.2 and 4.3 over here for the ratio. So it's 8.2. Let's go back over here. So that's 8.2 picofarads. Remember, your answer will be off by just a little bit if you don't put that in there. So then that's 4.3 for the ratio. So then if we take 8.2 pico divided by 4.3 equals, I got 1.91 if I round, 1.91 pico farads. So that's all there is to that. So what you're going to be seeing on the quiz is some more of that. Oh, I've got one more here. So let's go ahead and do one more. So C20 equals C2 nominal. So if we go back over to C2, and that was 830A. Okay, so that's going to be 10 picofarads at 4.5. All right, so 10 at 4.5. Okay, so that's going to be 10 picofarads divided by 4.5, which is the ratio. So 10 pico divided by 4.5 equals, and that should be like 2.22 picofarads. So the range in capacitance for each one of these, you'll see the one, this one right here is 2.22 picofarads to 10. This 829A is from 1.91 picofarads to 8.2 picofarads, and that's from 2 to 20 volts. And 833A is 6.6 picofarads to 33 picofarads. And the 832A, which is the one out of the book, is 4.4 picofarads to 22 picofarads. So anyways, this right here is all we've got for this lesson. That is the main thing is trying to show you that with because they're voltage controlled, I mean you can control the amount of capacitance with these diodes. So that's the whole reason for doing the formula and showing you how you calculate it and show you that here's the ranges that the capacitance can range from. So I think that there is it for this lesson. Be on the lookout for a quiz, and I'll see you on the next one. Thanks.